All right, so let's continue our discussion of discretizing boundary value problems using finite differences. So as you recall, it's like where we had left off was that we had written down this linear system of equations as a discretization of the general linear case of boundary value problems. Okay, and you have sort of this system of equations in matrix vector product here. So the first question then to ask is, well, under what circumstances this linear system has a solution? Okay, so let's sort of make some remarks on this. So if you assume that these VJs are positive and that h is small, okay, small enough. And in particular, what I mean by small enough is that the absolute value of 1/2 HWJ is less than 1 for all the j's, then the following is true. And what happens is that the absolute value of 2 h squared Vj is greater than the absolute value of 1 plus 1/2 HWJ plus 1 minus 1/2 HWJ. And this is 2. Okay. So the basic idea, if you will, is the following. Okay. So under this assumption, all right, which gives you a constraint, it's like on how h is, and the assumption that Vj is greater than 0, and what this condition is basically saying is that, so if you look at this, obviously, this is the absolute value of the diagonal entries, right, and then these are the the entries, the aj's and the cj's, all right, while the a's and c's, it's like out of the corresponding rows. And so basically what that's saying is that the diagonal entry dominates the other entries in the row, which is obviously this notion of diagonal dominance. Okay, so this implies that the matrix is diagonally dominant. And hopefully you recall from our, it's like your previous courses on numerical linear algebra that diagonal dominance is sufficient to guarantee that the solution of the linear system exists. Okay, so which means that the solution exists. Okay. All right. So that's one thing here. So let's now talk about convergence, right? So far it's like all we've said is that if you have this linear system of equations, that if again these VJs are positive and h is small enough, again with respect to this WJ term, right? Then that linear system has a unique solution. Okay. And so now you still have to ask whether or not the solution of that linear system of equations is going to converge in some appropriate sense to the solution of the original boundary value problem. Okay, so that's the second question we'd like to ask, right, which is convergence. Right, so when h goes to 0, right, the discrete solution should converge, right, in sort of a pointwise sense to the continuous solution of the boundary value problem. Okay, so if x of t is the true solution, And what you'd like to show, if possible, is that x at tj minus xj, right, converges to 0. So you still have to check that as h goes to 0. Okay, so let's try to explore. It's like this question here. You have convergence. It's like pointwise in this sense. It's like as h goes to 0. Okay, so towards that end, it's like I'm going to write down an error, right? So ej is going to be x at tj minus xj. Okay, so I'm going to write down an equation like this, and sort of the intuition, if you will, is that given what you know about the exact solution and what you know about the numerical solution, we're going to try to write down an expression. It's like which the error term satisfies, and then show that with that in mind, right, the error goes to 0, right, as h goes to 0. So that's sort of the general framework of what we're going to try to do now. Okay, so so essentially what's going to happen then is that I'm going to write down an equation for an equation which the continuous solution satisfies, and an equation which obviously the discrete equation satisfies. So the first thing is to write down an equation the continuous solution satisfies. Again, the way to sort of think about this is that you're going to rewrite the original differential equation in terms of finite differences involving the exact solution now, but with the additional error term. It's like in coming from the analysis. So, so you know that sorry, I think, yeah, so I should call this y. I think we changed notation a bit somewhere here. So y of t is the true, y of x is the true solution, and we want y at xj minus yj to converge to 0. And let's call ej y xj minus yj. Okay, all right, sorry. Okay, so so you have y at tj y at xj plus 1, right? No. Okay. Let me just write this as y at xj minus h minus 2y at xj plus y at xj plus h over h squared, right? Okay, and I'm going to write down the error term explicitly. This is minus 1 over 12 h squared, fourth derivative of y at some unknown point. Let's call that tau j. Right, is equal to uj plus vj y xj plus wj y at xj plus h minus y at xj minus h over 2h minus 1/6 h squared, the third derivative of y at some unknown point. Okay, so this equation is exactly satisfied because we've replaced the derivative terms. It's like with the corresponding sort of Taylor, well, with the corresponding, it's like finite difference. It's like, but with the remainder term as well. Okay, all right. So that's an equality. Okay, so that's the equation which the continuous solution evaluated at the points xj satisfy, and then it's like you have the sort of second equation, which is sort of just the defining equation for the discrete solution. So yj minus 1 minus 2 yj plus yj plus 1 over h squared is equal to uj plus vj, yj plus wj, yj plus 1 minus yj minus 1 over 2h. Okay, so subtracting the first from the second equation allows you to write down now an equation involving the error terms. Okay, so 1 minus 2 gives me that ej minus 1 minus 2ej plus ej plus 1 over h squared is equal to, okay, vj ej plus wj ej plus 1 minus ej minus 1 over 2h. All right. So you can see that the uj cancels out, so I don't have the uj anymore. But there's sort of this sort of remainder term. It's like associated with replacing the derivatives. It's like with this finite difference, right? So that's going to be incorporated in this last term here, plus h squared gj. Okay, where gj is equal to 1/12 fourth derivative of x at tau j minus 1/4 derivative of y plus the minus 1/6 the third derivative of y at cj. Okay, so those are the error terms. So I can rewrite that as before. It's like by multiplying by h squared throughout, right? By as following: minus 1 minus 1/2 h wj ej minus 1 plus 2 plus h squared vj ej plus minus 1 plus 1/2 h wj ej plus 1 is equal to minus h to the 4th gj. Okay, so you can sort of see where this is sort of heading, right? Yeah, so basically what happens, if you will, is that the sort of the error terms, it's like satisfy a linear system of equations where the coefficient matrix is the same as the one you have before, but the right-hand side, right, it's like it's different. Okay, and in particular, as before, it's like you will have to sort of, yeah. So, and then the other thing, of course, is that the boundary conditions for the error, right, is that E0 is equal to 0 and En is equal to 0. And that's because you're using, it's like the exact boundary data, it's like for y0 and yn, if you recall, right? So there is actually no error, it's like in the boundary terms here, okay? So normally it's like if they were sort of non-trivial boundary values, if you recall, they'll show up on the right-hand side when you write down this linear system of equations. And that's because it's like, it's like if you write this equation down for j equals 1 to j equals n, the j equals 1 case and the j equals n case will involve a E0 and En term. So you have to move that to the right-hand side. But in this case, it's like E0 and En are 0, so you just have this kind of equation. So at a high level, it's like what you're really seeing is that you have a linear system of equations, and that matrix is invertible, right? But that right-hand side is going to go to 0 as h goes to 0. So what you would expect then is that, it's like this vector of error terms, E1 to En, would then also go to 0 because this matrix is invertible, basically. All right, so that's more or less the main argument, it's like which follows. Let me try to, again, make this more precise, okay? So you can rewrite these again in terms of the notation we had before, right? So in the previous notation, what you have is that you have aj minus 1, ej minus 1 plus dj, ej plus cj, ej plus 1 is equal to minus h to the 4 gj. Okay. So I denote by lambda sort of the value of each a, it's like which is sort of the little infinity error, right, of this thing, right? So E is equal to E1 to En. So basically what I'm saying is that lambda is the maximum error, okay? All right, so you have that dj, ej in absolute value is less than equal to h to the 4 absolute value of gj plus alpha j minus 1 ej plus ej minus 1 plus cj ej plus 1. Okay, so that just comes from looking at this term. It's like, and then using the triangle inequality when you take absolute values. Okay. All right, so in particular, right, what that's true is that dj lambda is less than equal to h to the 4, the infinity error of g, right, plus absolute value of alpha j lambda plus cj lambda. Okay, so I can then write down an expression for lambda. Lambda multiplied into absolute value dj minus absolute value alpha j minus 1, sorry, aj minus 1 minus absolute value cj minus 1 is less than equal to h to the 4th infinity error for g. And then this is positive since we have, at least for a sufficiently small h, right, since the matrix is diagonally dominant. Okay, all right, so all right, so we make the following observation. So observe that the absolute value of dj minus cj minus aj minus 1 is equal to 2 plus h squared vj minus so this is just h squared vj, all right. Right, so again, this equality holds only when h is small enough. It's like, but under that condition, you just get that equals h squared vj, right? So I can write this as lambda vj h squared is less than equal to h to the 4 infinity norm, it's like of g, okay? So this means that lambda is less than equal to h squared infinity norm of g divided by the infimum over v of x. And then this is a constant. So what that means is that lambda is big O of h squared, and in particular, it's like as h goes to 0, it's like lambda will go to 0. But lambda is sort of, again, the maximum error you have pointwise of the solution. So what that allows you to conclude then is that as h goes to 0, right, the discrete solution of this finite difference based discretization of the boundary value problem converges pointwise to the exact solution of the boundary value problem, okay, which is what we set out to prove. So let me just stop here for now.